Okay, so welcome back, everybody, to algorithms. And today's today's topic is DP 101, dynamic programming, the first introduction lecture to dynamic programming. As you all know, dynamic programming is the most important topic in a graduate algorithms class, and we'll spend like at least 2 weeks on it, 2 or 3 weeks on it, and we'll see a lot of other applications of DP in graph algorithms chapter. So DP is the most important topic that you will learn in this whole course. And also DP is probably one of the most important discoveries or inventions ever made by human beings in the history of human civilization. Like if you were to show off human civilization to aliens, I would say DP is one of the topics that you would definitely include in your list of discoveries. Okay, so what is DP? Well, everybody have heard of DP, I hope, in this class. But what is the kind of one-sentence summary of DP? Well, I listed on the slides. You can see that DP is very much like divide and conquer or recursion, which we have dealt with a lot in the previous chapter of data structures, like merge sort or quick sort, right? But of course, DP is a bit more than that, right? So what's that bit that is extra over divide and conquer? Well, I would say it's caching, and a lot of people understand that caching is due to overlapping subproblems, but I'll explain it. It's actually not due to overlapping subproblems. It's actually due to multiple divides, which causes overlapping subproblems. We'll see that bit by bit. But here is the picture of divide and conquer, which you all know, that you divide one big problem that is too big for you to solve at once. You divide it into two smaller subproblems, which are much smaller in size. You solve it recursively, and you solve that recursively, and then after you call the recursion, you get reported by your children of the solution of the subproblem and the solution of this subproblem, and then you try to combine. So it's always divide and conquer and combine into a big solution for the whole problem. Okay, that's good. That's recursion. That's divide and conquer. But notice that there is only one divide. Whereas DP has multiple divides. In this case, I drew 3 different kinds of divides for the same problem. Okay, so this is not 3 different problems. This is the same problem. I just divide it in 3 different ways. I just partition it in 3 different ways. Think about the partition function in the partition step in quicksort. There's only one way of partitioning for a given pivot, right? So the partitioning is deterministic. You always partition. If the pivot is somewhere here, it always get like this kind of partition. But in DP, we'll try many different kinds of partitioning. So I divide it this way first, I divide this way second, divide the third way. In each divide, I will call the 2 recursions, two conquers to conquer the subproblems, and the combine. So that after I combine the first divide, I got one solution for the whole subproblem, for the whole problem, and I got another divide, and I call the 2 recursions, and I combine the 2 solutions to form another solution for this whole problem. And then I got a third solution for the third. And then I have to kind of unify or summarize between the 3 solutions. That's another operation that is not found in divide and conquer. I have to kind of compare across 3 different solutions and report to my parent the best solution or the total solution or whatever. Okay, so that's why DP is one step beyond divide and conquer. Okay, so here we have only one divide, and the subproblems are non-overlapping subproblems, or we call it disjoint, non-overlapping disjoint subproblems, because you never would have, like in merge sort or quick sort, you divide the array into 2 subarrays. These 2 subarrays are definitely disjoint. But in DP, because you have multiple divides, then you would have overlapping subproblems, because this problem and this problem are overlapping, and this problem and this problem are overlapping, right? So you have overlapping subproblems. And because of that, you need caching in order to avoid repeated calculation of your same subproblem over and over. And this will not happen in divide and conquer, because in divide and conquer, every time you got disjoint subproblems, there's never overlapping issue, and there's never a need for caching. Okay, so this might be a little bit too dry of an introduction. So let's look at one particular concrete example of DP. Well, what kind of examples do you want to introduce with DP? If you want to introduce DP to a, let's say, 5-year-old or 7-year-old, like let's say your nephew or niece is 5 years or 7 years old and asks you, what is DP? Can you explain DP to me? Which example would you choose to explain DP to your 5-year-old or 7-year-old nephew or niece? Well, the answer is, well, it's actually quite surprising. The answer is Fibonacci. So Fibonacci series is our by far the simplest example, and the first example you should use to introduce DP. Okay, so what is Fibonacci series? Well, everybody knows that Fibonacci is just a series. Well, it starts, by this Italian mathematician called Fibonacci, who studies the reproduction numbers of rabbits, because rabbits reproduce really fast. So every monthly, the rabbits will reproduce a lot. But anyways, he summarizes that there is a relationship that if you have certain number of rabbits in this month and last month, and then you can calculate how many rabbits you have in the next month. Okay, so every fn is the sum of the previous two numbers, fn and n minus 1 and n minus 2. So if you just look at this equation, it's definitely a recursive equation, and you can calculate it recursively, and we can write a program to do that, just the Fibonacci program that I'm displaying on slides. It's very simple, right? It's a few lines of code, except that it's very, very slow, right? Why it's very, very slow? And you can try it. It is really, really ridiculously slow, right? And if you write a recursive program like that, you probably will need like a long time to calculate, even for a small n, like say 20. And the reason why is because you're doing a lot of repeated calculations in naive implementation of this recursion, like as I showed on the slides, right? Because let's look at it. So f of, say, 5 is made up of f4, Fibonacci of 4, and Fibonacci of 3, okay? And then f4 is a combination of f3 plus f2, and f3 is in turn is by itself a combination of f2 plus f1, and so on and so forth. And then this, you also have f2 plus f1, and go on and on, right? And you notice that a lot of these problems are repeated, of course. For example, if you call the recursion, f5 first called f4, f4 will ask what is f3, f3 will ask what is f2, and f2 will report, because f2 is at the end of the boundary, the condition at the end of the recursion. It will report, oh, my number is 1, let's say back to f3, and then you'll call this number f1, and f1 says, oh, my number is also 1, and then f3 figures out that my number is 2 to report to its own parent, and so on and so forth, right? And then your recursion will go here, go back here, and then goes here to ask f2. But f2 has already been calculated here down below, right? So this is a repeated subproblem. So you should avoid doing that, but nevertheless, you actually still did it, even though it doesn't look like a lot of repetitions, a lot of kind of redundant calculations, because it's only one level of recursion. It's actually at the end, so it's a leaf node, so it doesn't kind of waste very much. But then you figure out that f4 is 3, right? And then f5 will call what is f3. This part is a big problem, because the whole subtree are repeated. The whole subtree is redundant because it's already calculated down below here. So we all know that anything that has been calculated before, it should not be repeated. So we should totally prune this whole subtree if we were doing it in a more efficient way, and prune this f2 as well. So anything that has been calculated will not be calculated again. We can do that. We all know how to do that. But if you don't know how to do that, then you would write a full recursion like what I had right on the slides right now. And that's why it's really, really slow, because a lot of the the same number, same questions like F2, F3, F4, F5, and you can imagine if you go to like say 100, how many repeated calculations are there, right? So there's a lot of repetitions. And as I wrote on the slides, if you can imagine, so let's say this is f of n, and f of n minus 1, n minus 2, and all the way down to 2 and 1. So this is f3 and so on and so forth, right? So in principle, only the leftmost branch should be computed, because everything else other than the leftmost branch will actually repeated, right? But because the recursion doesn't know that, it kind of tries to compute everything in this triangle. Well, not as bad as that, because as I drew on the slides, it's actually more like a kind of a half triangle, because on the leftmost branch, it decreases by 1 every single time, like say from 5, 4 to 3 to 1, to 2. But on the rightmost branch, it decreases by 2 every single step, because this number will be n minus 2, and this number will be n minus 4, and this n minus 2, and so on and so forth, like 5, 3, 1, right? Because it's minus 2 on the rightmost branch. So actually, this part is empty, so we don't need this part. So the recursion isn't as bad as that, but it still is very bad, because it's kind of not as bad as the full triangle. And if it were the full triangle, it would be like 2 to the n, right, complexity. But it's not. So this is all the way to, let's say, to 1, right? It's not as bad as that, right? Because it's right like kind of a half triangle. So it's actually, how bad it is? Well, it is 1.618 something to the power of n. And what's that number? That number reminds you of the famous golden ratio, which is like square root of 5 plus 1 divided by 2. Okay? And Fibonacci series does have a deep connection with the golden ratio, which I will not expand. We don't have time to expand to that. It's very interesting. You can look up on Wikipedia or anywhere on the web. But anyways, it's roughly speaking 1.6 something to the power of n, which is still exponential. So this number is still exponential. That means it's really, really slow, right? You know, that's why if you have n of 100, it will take like maybe over a year, or I don't know how long to calculate just that number. And we all know that it shouldn't be the case, right? Because before learning DP, we all know how to solve this equation in a much faster way. And can anybody tell me what is the much faster way of writing, of solving the Fibonacci? Probably without recursion, right? Yeah, like maybe back in very first course in computer science or programming, you know how to write a for loop. Just write a for loop for that, and that's something like I wrote maybe here in the middle. So you just write a for loop, or in the lower left corner on the slides. You can write a for loop, and it's just the on time for loop. It should not be as bad as 1.6 or some exponential complexity. It should really be on, right? It should really be on. But how do you achieve this on with recursion? So we want to kind of keep the recursive structure, which is nice because this is defined recursively. It's divide and conquer. We should think about it in a top-down fashion. But we also don't want to go all the way to exponential time. So we want to achieve the merits of both worlds. We want to be fast, and we also want to be, beautiful and simple, right? So we want to do recursion, but still in linear time. How do we do it? The answer is very simple. We do recursion, like divide and conquer, but we avoid overlapping subproblems by a technique called caching. And I'll write it in yellow. By caching subproblems. By caching the problems that you have already solved before, I've already solved before, you don't need to solve it again. And this caching is usually done by a hash table, which is in Python called a dictionary, because you need to look up what kind of problems that you have solved before. Okay, so let me show you this program. So that DP1 is top-down with memoization. So this is also called memoization. It's kind of a French word. It's not memorization, it's memoization. It's a special term in computer science, which just means caching. It's not fancy at all, even though it looks fancy on the surface. So I just use a dictionary, a hash table, to record the numbers I've solved before. So initially I had it like Fibonacci of 1 maps to 1 and 2 maps to 1. And then if n is not in fibs, which means I encounter a new problem, like on the leftmost branch, I always call recursion, I'll do the divide and conquer. But otherwise, if n is in fibs, that means n is not a new problem and n is an old problem that I've seen before, then I don't call recursion. I just look up the lookup table, the cache, the hash table, and I just return fibs of n. Okay, so that technique of memoization or caching made sure that every problem is solved at most once, right? Or if it's needed, it's solved once. If it's not needed, it's not even touched. And there's never a case that a problem is solved twice or 3 times. Okay, and once you do that, your complexity is no longer exponential but back to linear time. Okay, so I wanted to take a look at the code I displayed on the bottom right corner of the slides, DP1, which is top-down with memoization in linear time, right? But alternatively, you can also do it in a bottom-up order. So dynamic programming can always be, approached in top-down versus bottom-up orders, 2 different methods, 2 different kind of orders. On the lower left corner and the bottom and mid-bottom of my slides, I displayed fib0 and fib, 2 different versions of fib0. The bottom left corner one is a single for loop. I don't need to remember anything. So in that case, I have a O1 space. Okay, so the very lower left corner, I had a fib0. Lower left corner, I have ON time and O1 space. And the second fib0, sorry, I should probably rename it fib01, fib0a, fib0b. The second fib0 in the middle side, the center of the bottom side of my slides, I have ON time and ON space, because I have an array or list or whatever kind of a sequence dictionary, sequence data structure, which is called fibs, and fibs got appended a new number every single time. So you always compute f minus 1 plus f minus 2, which is the last 2 numbers in your list, and you append it to the end. So this is very cool. This is f, and I should use another color, f of -1 plus f of -2. Okay, this is very cool. This corresponds to this. And that gives ON time, but also ON space, because you have to store all the numbers, F1, F2, all the way to Fn. Okay, the lower left corner program does not even store it. It's actually using O1 space. It only stores the last 2 numbers, but it forgot everything else. So that's also a very cool technique. Oftentimes, if you need more space, you need a trick that is saving space, but of course, not saving time, but saving space. And the fib1 that I wrote on the bottom right corner is a recursive version, but because of the caching, it's also ON time and ON space, and that's more similar to the fib0, to the second fib0. Okay, so in any case, all the 3 versions are not exponential but linear time. Okay, any questions for Fibonacci? Okay, I assume everybody understands this very well, but let me ask you this question. Why is this a dynamic programming with multiple divides? And we know this is not a simple divide and conquer, because if it were a single divide and conquer, we wouldn't need to use any caching. It would just, it will not be exponential time. It will be like, n or n log n or n squared or whatever, those complexities, like you do merge sort or quick sort, It's totally not a divide and conquer. Even though it totally looks like a divide and conquer. Oh, I divide it into two subproblems, n-1 and n-2. You would attempt to think that way, right? You would try to think, oh, this is an instance of divide and conquer. No, it is not. I'll show you why it is not. Because if it were a divide and conquer instance, then you wouldn't have any overlapping subproblems. But here, obviously, n-1 and n-2 are two overlapping subproblems, obviously, right? So it's not the disjoint partitioning that you saw in merge sort and quick sort and heap sort, anything, right? In all those divide and conquer examples we saw in data structures, once you divide, it's disjoint, and that's only one divide, okay? And here, the two subproblems are overlapping. What does that mean? Well, that means they're not two subproblems in one divide, but rather two different divides. Okay, so that's the most important lesson I want you to notice. So this is two divides, not one divide with two subproblems. So two different divides. Okay, so this plus is not the combine operator. Like you sort a merge sort left, merge sort right, and then I merge sort it. I do the concatenation. That plus is not that concatenation operator, but rather a summary operator across different divides. Okay, so then what is f of n-1? So f of n-1 itself is one divide. Okay, that's one divide. So it divides the problem into, it divides the subproblem into, I would need some space here. Okay, so let's remove the exponential part. It would divide the subproblem into, I take out 1, and then this is n-1. So that's the first divide. Okay. And what about n-2? Well, that's another divide, which is take out 2 guys. And I do recursion onto a subproblem, which is n-2 in size. Right? So these are two different divides, rather than one divide with two different subproblems. So these are two different divides, but each divide has only one recursion, one subproblem, one conquer. It's more like the quick select or binary search problem, where you only have one child to do recursion on. Like you have only one child, okay? But you have two different divides. That's the difference, right? Two different divides, but each divide has only one child to do recursion on. Okay, and what about this operator here? This operator is the summary operator, not a concatenation operator. It's the summary operator that combines, that kind of summarizes the solutions, the individual solutions from different divides, right? So this operator we've never seen before in divide and conquer, because there's no need. There's only one divide. It's unique, either fn-1 or fn-2. There's never the case that you have both n-1 and n-2. So we never had this operator here. All we had is a concatenation operator between the two. And from now on, we'll call this concatenation operator the times operator, and the summary operator the plus operator. So this is the concatenation operator. So you have a concatenation operator here, so divide and conquer and combine, or in other words, combine. But across the three different divides, you need another operator, which is this operator, the plus operator, which is called a summary operator. So let's do this. I'm not sure if you can see it on the board. So between different divides, you use this summary operator. So this is called a summary operator. Okay, so from now on, we'll have to, very importantly, distinguish these two operators. Okay, and you'll see more examples where you will have two different operators. But you might ask, in my Fibonacci question, where is my concatenation operator? Is there any? Well, because there's only one-sided recursion, like in quick select or binary search, looks like there's no the concatenation or combination operator because you only have one child. So whoever returns, you just take it, right? It looks like there's no need to do any operation on it. No need to do any kind of add 1 or plus 1 or add 1 or minus 1 or whatever. We'll see later that the times operator is actually times 1 here. That's the operation here. It's just kind of verbatim. It's identity. But in other problems, we'll see differently. Because there's only one-sided recursion, there's no, really you can imagine there's no combination operator in this very simple problem. But in other problems that we will see very quickly, there is a real operator like this combination if you have two-sided division. Okay, two-sided recursion. Okay, very good. So yeah, so this is the summary operator, not the concatenation operator. Okay, I would stop here and take any questions. Okay, thank you.